Well, hello everyone. Today's topic is going to be Introduction to Polynomials. It's the first part of Chapter 5. And let's begin by writing down an example of a polynomial function. So this is a polynomial function. It's basically any expression, formula, function that has nothing but positive powers of x. The constant term does count because essentially what that looks like is 2x to the 0. So plus 2 is part of that feature. And when you look at a polynomial, sometimes you refer to what's called the degree of the polynomial. And the degree of the polynomial is the largest power of x. And it's a number, so you just write down 3, because the largest power of x here is x cubed. So that's a term. We very often call these numbers here, for instance, the 4, the 2, and the 7, or the negative 7. And these are called coefficients. So for instance, the coefficient of x cubed is the number 4. The coefficient of x squared is 2. And the coefficient of x is negative 7. We have a different name for the last term, the plus 2, minus 10, that kind of number, and that is called the constant term. So in this case, it would be positive 2. So we've got a little bit of vocabulary. These are called polynomials. The largest power is called a degree, so this would be a polynomial of degree 3. And we even can talk about the coefficient of x squared or the coefficient of x cubed. And you'll realize when I say that, I'm talking about the number 2 or the number 4. And we can talk about the constant term of this particular polynomial. In this case, it's plus 2. So let's evaluate a polynomial. So if I asked you to calculate f of 2 of this polynomial, basically x is going to get replaced by 2. So it's 4 times 2 cubed plus 2 times 2 squared minus 7 times 2 add 2. And you could certainly do that on your calculator. So let me just show you how you would do that in one go. So you'd go 4 times 2 raised to the power of 3. So that's 4 times 2 cubed. Add 2 times 2 squared. Take away 7 times 2. And then finally finish with an add 2. And the number that we got here is 28. Now, if you think of this function is basically it's saying, you give me an x, and I'll tell you the value of f of x. And I want you to think of the value of f of x as the y coordinate. So if you give me the x, I'll tell you the y coordinate. So in this example here, the x was 2, and the value of the function was 28. So this would correspond to a point, roughly way up here. Right, imagine that's 2. This is 28. This would represent 1 point on this function. Now, if you plotted lots and lots and lots of them, you could eventually get the entire graph of it. Now, I wouldn't want to do that by hand. That's why we have programs like Desmos. But essentially, if you give me an x, the value of f of 2 is the y coordinate you would get. So the value of f of 2, which is 28, is also the y coordinate you would get. So when x is 2, the y coordinate would be 28. let's move on and look at graphs of various polynomials. And for instance, if I gave you a polynomial p of x and it was 2x squared plus 3, then you might want to graph it. Now, you could certainly spend a lot of time doing that by a table of values. So you could do something like this. So when x is -2, when x is -1, when x is 0, when x is 1, and finally when x is 2. Now that'll give you a little snapshot of what this would look like. Now, I would like to at least speed things up a little bit. So if I wanted to do a lot of calculations with the same function, you can go and you press y = on your calculator. And then you type in this case, 2x squared plus 3. Then you only need to do this once. Once you've done that, do second button. Where is it? Table. Here. And make sure that it looks like what you see in front of you here. In particular, the independent variable should have highlighted. And then you do second button, table. And if there's stuff there, just hit the delete button. And now you can type in what you want. -2, -1, 0, 1, and 2. And that's just quicker than doing each one separately. So this would be 11. This would be 5. This would be 3. This would be 5 again. And this would be, what, 11. And that would basically correspond to a set of points that we know are on the curve. And then if I had good square paper, pretend this is, I would then plot the 5 points that I've got and join them with the best, smoothest curve I can find. So let's pretend that's -1, that's -2, there's 0, here is 1, here is 2. I need to go up to 11, so 2, 4, 6, 8, 10, 12. I'll use a little scale. Let's see what we get. -211 would be about here. -15 would be about here. 0.3 would be definitely here. Then you go back and do 1.5 and 2.11. And then kind of a nice curve that looks like this. And this would be what the graph of that guy would look like. Now there's a much nicer way, and that is to use Desmos. So I'm setting up Desmos right now so that I can do it. And let's check it out. So stop this guy, go into Desmos, and you can type, in this case, p of x equals 2x squared plus 3. And if I move things around a little bit, there. This is essentially the same curve that I had. Now, the fact my curve might have looked a bit wider is all to do with scales. You know, if you do one box represents 1 vertically, you would get the graph that looked identical to that. But what you notice is it is a concave up happy face shape, and it passes through the y-axis at 0.3. And that is essentially 2 different ways in which you can draw a graph of a polynomial function. But this polynomial function has degree 2. doesn't have any x term, we sometimes call this particular special case a quadratic function. So when it's got x squared in it, it's a quadratic function. Let's see what we need to do next. And well, in the homework, what you typically get here, and let me show you one of the homework questions, is that you get 4 pictures and you choose the one that looks like it. So for instance, in this case here, let me just double check that I'm actually in. Yes, I am. Right, if you wanted to do this one, you would plug it into Desmos, and one of these 4 pictures that you see here would correspond to that guy. And let's just pretend it's that one, then you click on that. Now, what we're looking at in question 5 then is a very simple application. And that is, if you're told that the distance of an object that will fall in t seconds is given by this formula, how far will it fall in 5 seconds? So if you were atop of a very big mountain, you drop something, how far would it fall according to this function? So you would go 2.735 multiplied by 5 seconds squared, so 5 squared. And I would go into my calculator and I'll tell you what I got from that. I got 2.735 times that guy, and it's 68.375. So 68.375 in that particular example. So let's see what we've done. We've introduced this function, this equation if you prefer, f of x, and it's a polynomial as long as it has positive powers of x. So this can be x to the 10 or x to the 2. It's not allowed to be x to the negative 2 power. It's not allowed to be the square root of x, which is a fractional power. It must be x squared or cubed or x on its own to count as a polynomial. And we looked at, if you want to evaluate a polynomial, you essentially just replace the x by whatever this number is. And if the function's in terms of t, you replace t by whatever that number is. So now we're going to deal with the algebra of polynomials. Not so much functions, just expressions. So if I gave you the polynomial 3x squared plus 7x minus 2, I'll put a bracket around it, and I asked you to add the polynomial 3x cubed plus 2x squared minus x, then what we really need to do here is combine these two and simplify them, collect like terms. Now, since there's a plus there, very little happens to the terms. This guy stays as plus 3x cubed, this guy stays as plus 2x squared, and this guy stays as negative x. You then do what's called collecting like terms. So you look for the biggest term, and it's 3x cubed. And then you have another look in case there's any other x cubes, but there isn't. So 3x cubed. Then we look for x squared. I have 3x squared plus 2 more. So I wouldn't normally write this line, but I'll put it in today. Now you combine them, you get plus 5x squared, and you still have 3x cubed. Now if we travel a little bit further, I have a plus 7x and a minus 1x. So when we collect the like terms, in this case the x's together, a plus 7 take away 1 leaves me plus 6x. And then in this case, we then finish with any constant. There is only one number, negative 2, so it is negative 2 all the way through. And we call that simplifying, right? Combining two polynomials into one. And you normally do it from biggest to smallest, which they call, it's an unusual term, but this is what they call that. They call it, the vertical format. So the vertical format just means biggest power, next power of x, next power of x, finish with the smallest. Now it's a little bit trickier. So I'm going to use the same two terms, but this time we're going to subtract them. And these brackets are really here to emphasize. You don't need to worry about the first term because there's nothing else happening to it. So this is still going to be 3x squared plus 7x take away 2. But now you're going to subtract all of that. So think of that negative as being distributed through everything. So you get a negative 3x cubed, a negative 2x squared, and finally a plus x. A negative of a negative gives you a plus. And these two are negatives of positives, so that's why they're negatives. Now we collect like terms. There is the biggest power, and there's only 3x cubed. I have a 3x squared, and I have a negative 2x squared. So you would write 3x squared, take away 2x squared. Now that would get you 1x squared, but we never write 1. 1x squared is just written as x squared. The implication is that if you only see an x squared, we all know it means there's one of them. You then move on to 7x and a plus x. So in this term, 7x, I have a plus x, and those combine nicely to get 8x. And then I have just a number negative 2 on its own. So here is the answer to those two being subtracted. This one here is those two being added. Hopefully you're cool with that. Now, there's no reason in the world why polynomial should only be using the variable x. So for my next one, I'm going to use the variable a. And this one is similar to question 11. So we have 5a squared take away 8a, subtract negative 3a squared, negative 8a minus 8. Nothing happening to the beginning of that, so this gets left alone. Subtracting a negative is adding 3a squared. Distribute that into that and you get a plus 8a, and that into that you get a plus 8. Now we'll collect like terms. The 5a squared plus 3a squared means you now have 8a squared. And that's as good as that's going to get. Something kind of nice is going to happen here. I have negative 8a plus 8a. Now what essentially happens here is that they kill each other off. And you might say, well, that means you've got 0 a's left. Well, I guess you do, but we never write 0a. 0a just means you don't have any a's. So you don't have anything. We don't even write plus 0 down because that's pointless. We just basically write nothing. They destroy each other. There's no contribution. And so all we have is a plus 8. And that is a simplified version. We have collected the like terms, and we've got this guy in our format they are interested in. Now, the next question, which is question 13, or at least one, like question 13, gets us to sketch a number of functions which are not identical but very similar. So the first one is going to be x squared. Then it's going to be x minus 3 squared. And then lastly, you're going to get x plus 4 squared. And we should get, if things work out well, some kind of relationship that kind of would help us to predict what would happen in other functions that look like this one. So let's go in, see what we have. So the first function was f of x, and it was equal to x squared. That's pretty nice. Next function is g of x, and it's equal to a bracket x take away 3 squared. Now I'm going to move this up a little bit. I'm going to click on that point there because I think that's quite interesting. I hope I got it. Yeah. And I'll click on that one there as well. And get a coordinate. There we go. When you look at the function f of x, which is the blue curve, and you look at the function g of x, which is the green curve, and I maybe have to move it down a touch, would you agree that they are identical in shape? They're just in a different location. And that 3 that was here, I'll have to put back now. Corresponds to that value there. Now, the next function we're going to put in is h of x. And h of x was equal to x plus 4 all squared. And if I shift this, shrink it just a little, there. Do you see that there is a distinct pattern going on for every one of these? They all have the same shape. They're just moved to the right or to the left by a fixed amount. So for instance, g of x is actually moved 3 spots, right? 1, 2, 3 to the right. H of x is actually 1, 2, 3, 4 to the left. You see, there is definitely something going on here. So I'm going to make up my own function, and I'm going to call it k of x. And I'm going to make these two guys go away, just so we don't get too much going on. And I'm going to make this x minus 1 squared. Before I finish drawing it, can you imagine where x minus 1 squared is going to be? Is it where you thought it was going to be? 1 unit to the right of x squared. If I put in another function, and I'll call it m of x, and this time it's going to be x plus, I don't know, 5. That's pretty big. All squared. There. Can you see it's moved? The blue curve, x squared, has now been moved 5 places. There you go. 5 places to the left. And so we can use the fact that certain families of polynomials, like this is a family, they all are members of the x squared family with something happening to them. We can predict what the sketch would look like without actually, plotting points or even using decimals if it was really being clever about things. I think that's kind of cool that you're able to do that. So, let's continue. So in that question, you would be asked to write down what the basic movement would be. So if someone gave you a question and went and said to you, m of x is x minus k all squared, where k could be any number, I would say that you move the function x squared k units to the right. So you can imagine that was x squared. Over here, at that point there, k would be x minus k squared. And that is us finished this topic. Hopefully it was helpful.